Hello everyone. Welcome to the Concepts of Engineering Mathematics course. In the previous lecture, we started our discussion with determinants. Then we saw how to solve the determinants or expand the determinants. We also saw concepts like minors and cofactors. And we saw some of the properties of the determinants, and towards the end we had seen the Cramer's rule for solving simultaneous equations. Okay, so let us now begin today's discussion with an example of the Cramer's rule. Okay, so we will solve a system of linear equations using the Cramer's rule. So we have now the question. So solve the system of equations. Solve the given system of equations using Cramer's rule. Using Cramer's rule. So we are given with three equations and we will be using the Cramer's rule to solve them. So our first equation is 2x minus 3y plus 4z equal to minus 9. So this is first. The next equation is minus 3x plus 4y plus 2z equal to minus 12. This is the second equation. And the next one we have is 4x minus 2y minus 3z equal to minus 3. So we are given with these three equations, and now we need to solve them using the Cramer's rule. So let us form the standard determinant of coefficients. Okay, so we now have the determinant m as this is 2 minus 3 4. Here we will have minus 3 4 minus 2. These are the first column is x coefficients, second column is coefficients of y, and third will be 4 2 and minus 3. Okay. Also we have k1 k2 and k3. So k1 is minus 9 here, k2 is minus 12, and k3 is minus 3. So we know that for Cramer's rule we need to find the determinant m, and then we will replace the coefficients respectively to find the unknowns. Okay, so let us first see the value of determinant m. So therefore determinant m is given as, let me directly expand it. So this will be 2 and this will be 4 3s are minus 12 minus 2 2s are 4. So this is plus 4. Okay. This will be minus minus plus 3 into 3 3s are 9. This will be positive, and then 4 2s are 8. So minus 8, and this will be plus 4. Again this will become plus 6 minus 16. Okay. So from here we get minus 8 into 2, that is minus 16, and this will be 3 only because 9 minus 8 is 1 and 1 into 3 is 3, and this will be minus 10 into 4, so minus 40. Minus 40. So this will be minus 56 minus 56 plus 3 So this will become minus 53. Okay. So we have these values. Okay. Now let us see the values of these unknowns. How are they calculated? So we have determinant of m as minus 53. Let me, okay, let it be. So therefore, now now x is nothing but replace the coefficients of x in determinant m by k1, k2 and k3. Okay, so here we will have minus 9, minus 12, minus 3, and remaining portion will be unchanged. So minus 3, 4, and then minus 2. Again here we have 4, 2, and minus 3. Okay, and this we will divide by determinant of m. So this will be nothing but let us say this is 1 over minus 53. This is the determinant of m, and this determinant now we can calculate. So this will be minus 9 into this is minus 12 plus 4. Okay. This is plus 3 into 36 plus 6, and this will be plus 4 into 24. Okay, so 24 and plus 12. So upon expanding this, we get the value of x as minus 1 by 53 into this is minus 12 plus 4 will be minus 8. So this is minus minus plus. So 72, and this will be 36 plus 6 is nothing but 42, and this will be 126. Okay. And this will be 24 plus 12 is 36, and 36 fours are 3 6 are 24, 4 carry 2, so 12, and this is 144. So again, upon solving this, we get this value as this is 6, 2 plus 6, 8, and then 4, 12, 2 carry 1. So 7, 1, 8, 8 and 2, 10, 10 and 4, 14 carry 1. So this is 1, 1, 2, 3, 42. So minus 342 over 53. Okay. Over 53. So we get the value of x as this. Is it correct? Let me check. Okay, so this is the value of x that we get here. Okay, similarly, let us calculate the value of y now. Okay, so this, let us write x as minus 342 over 53. Now y is nothing but we will now change the coefficient of y in this determinant. Okay, so we have 2 minus 3 4. So 2 minus 3 4. Here we will put minus 9, minus 12, and then minus 3, and last column will be unchanged. Okay, so 4, 2, and minus 3. Okay, and in the denominator we will put the determinant of m, which is minus 53. So here we have minus 53. So if we solve this, this is 1 over minus 1 over 53, and again here we have these values as, so 2 into 12 3s are 36, minus minus plus, and this is again minus minus plus 3 to the 6. Okay, and this will be plus 9 times 3 3s are 9 plus, and this is 8 minus 8, and this will be 4 into 9 plus 48. So upon calculating this, what we get is minus 1 over 53, and here we will have 42 into 2, that will be 84, and this will be 9, and again here we will have 57 into 4, so that will be 8 carry over 2, and that will be 22. So this now becomes, summing it up, we get 1 and carry 2, so this will be 10, 10, and 2 will be 12, carry 1, so this will be 321 minus 321 over 53. Okay. So this is the value of y that we get. Similarly, we can get the value of z also. Okay, so we have z as, z is given as, again the same determinant, but in place of coefficients of z, we will put k1, k2, and k3. Okay, so determinant is 2 minus 3, 4. So this is 2 minus 3, 4. Then we have minus 3, 4, minus 2. We have minus 3, 4, minus 2. And k1, k2 is minus 9, minus 12, and minus 3. So this is minus 9, minus 12, and minus 3. Okay. And in the denominator, we will put the determinant of m. Okay, that was minus 53. Okay, so upon solving, this will be, let us expand this determinant. So this is 2 times, this is 4 3s are 12, and minus minus plus, so this is again minus, because ultimately we have to subtract. So 4 3s are 12, and 12 2s are 24. Then we have plus 3 into, this is 9. What is happening? 9, and then minus minus plus, so 48, and then we have minus 9 into 6 minus 16. So upon solving this, we get the value of z as minus 1 over 53 into, this will be minus 36 into 2, so this is minus 72, and again we have 3 into 57, so this is positive, so plus 3 7s are 21, carry 2, 171, and this will be minus 10 into minus 9, so plus 90. Okay. And if we solve this, what we get is, so z is basically minus 1 by 53, and this is minus 72 plus, this is 261. Okay. And if we subtract 72 from it, what we get is minus 1 over 53. Okay, let me erase this, and so this will be 9 and 8 1 minus 189 over 53. So this is the value of z. So in this way we can solve the simultaneous equation in three variables using the Cramer's rule of determinants. So this was an example for the same. So with this, we will conclude our discussion on determinants, and we will use these concepts frequently in the coming discussion wherever required. Okay, so now let us begin our discussion on matrices. Okay, so let us see what we mean by matrix. So now let us begin. Matrices, okay, or matrix. So matrices are also arrays, and these are rectangular arrays which are ordered type. Okay, so these are ordered rectangular arrays of rows and columns. Okay. Rectangular means here it is not necessary that the rows and columns must be equal. Okay, so rows and columns. And here number of rows and columns are not necessarily equal, are not necessarily equal. So this is something different from determinants in case of matrices. Okay, so number of rows and number of columns may be different. And if they become equal, then the matrix will be called square matrix, as we will see a little later. Okay. So the way of representing a matrix is using a symbol like square brackets. Okay. So some enlarged brackets will enclose the rows and columns here. Okay. So suppose we have a matrix A, then it is represented as say A11, A12, A13, A21, A22, A23, A31, A32, and A33. Okay, say we have one more column, A14 here, A24 here, and A34 here. Okay, so this indicates that it is not necessary that rows and columns are equal in number. So this is a matrix, and again here we can write the order of the matrix. So firstly, the number of rows is written and then followed by columns. So this will be a 3 by 4 matrix. Okay. So there are 3 rows and 4 columns here. So A is a 3 by 4 matrix. This is how it is denoted. Also, it can be written as Aij, where I again stands for rows and J is for column. Okay. So Aij, where I is for row and J is for column. Okay. This is how it is represented. Okay, so now let us see various types of matrices. Okay. Means how these matrices are classified. We are now going to see various types of matrices. Various types of matrices. Okay. So very first one is a row matrix. Okay. So it is clear from the name that a row matrix will have only a single row or only one row. Okay. So we have a row matrix first. So row matrix has only one row and it may have any number of columns. Okay. So it has only one row and can have any number of columns. Okay. So this is something like, say we have a matrix, say A, which is nothing but say 2 -3 -3 6 and so on. So it may have any number of columns, but it will have a single row. So this is a 1/4 matrix. Okay. Here there is only one row but four columns. So any matrix which has dimensions or order like 1 into j is called a row matrix, where j can be any number. In fact, it will be generally greater than 1 because a 1/1 matrix is something different. Okay. So this is a row matrix. Then we have column matrix. Okay. So again, it is obvious from the name that it can have any number of rows but will have only one column matrix. Okay. So it has only one column and can have any number of rows and can have any number of rows. Okay. So let us see an example of a column matrix also. So suppose we have a matrix B like this, which has say elements like 1, 4, 2, 7 and so on. Okay. So this is a matrix where we have, let me keep it a 3/1. So every time we are using the second dimension as 4. So this is a 3/1 matrix. Okay. So here we can see that the number of columns is fixed as 1. So and number of rows can be anything. So it will have dimensions like I cross 1 or I into 1. Okay. So I may be 2, 3, 4, 5 and so on. So this is column matrix. Now next we have null or zero matrix. Okay. So third one is a null or a zero matrix. So it may have any dimension, but all the elements of this matrix will be 0. Null or zero matrix. Null or zero matrix. So here any matrix in which all the elements are 0. So it can be matrix of any order in which all the elements are 0. All the elements are 0. So let us say an example. Say again, we have a matrix C where all the elements of the matrix are 0. Okay, so this is a 2 by 5 matrix. There are 2 rows and 5 columns, but all the elements here are 0. Okay. So this is the third type of matrix. Now let us see the next one. So we have now the most important square matrix. Square matrix. Why I said it is important is because on a square matrix we can perform the operations of determinants also, because a determinant can be written for a square matrix as this matrix has the number of columns equal to the number of rows. Okay, so this is a matrix which has number of rows equal to number of rows equal to the number of columns. So any matrix Aij will be a square matrix if I equal to J. Square matrix if this I is equal to J, that is number of rows equal to number of columns. Okay, so suppose we have a matrix of order 2 by 2, then this is like 1 2 2 1. Okay. Suppose we have a matrix 3 by 3, so this is a third order square matrix. In this we will have elements like 1 2 3 4 5 6 7 8 9 etc. Okay. So this is a 2 by 2 matrix, this is a 3 by 3 matrix. Here we can see that the number of rows and number of columns are equal. Okay. So this was square matrix. Now the next type is diagonal matrix. Okay. So next we have a diagonal matrix. And what happens in diagonal matrix is any matrix in which all the elements except the principal diagonal are 0. Remember, the diagonal matrix will first be a square matrix. Okay, so any square matrix in which all the elements except the principal diagonal are 0 is known as a diagonal matrix. Okay, so diagonal matrix is a square matrix with all elements except those of principal diagonal are 0. Okay, so let us say we have a matrix D. Definitely it will be a square matrix. So say this is 2 7 6 and all other elements here are 0. So this is a 3 by 3 square matrix with all the elements except diagonal ones as 0. Okay, so you can see here that the diagonal elements here are non-zero only, and all other elements are 0. So this is a diagonal matrix. Now the next one is a scalar matrix. So scalar matrix is nothing but this is again a diagonal matrix in which all the diagonal elements are same. Okay. So they will have a similar or single scalar value. In that case, it will be a scalar matrix. So scalar matrix, and it is a diagonal matrix. Diagonal matrix with all diagonal elements equal. So suppose again we have the matrix D, but in this case now all the elements will be same diagonal elements. Okay, so say this is 700, this is 070, and 007. So this is a diagonal matrix of the order 3. Okay. So here you can see that this is a diagonal matrix because all the elements except the diagonal are 0, and it is also a scalar matrix because all the diagonal elements are same. Okay. So this is an example of the scalar matrix. Now next we have the identity matrix, and it is also a very important one. So we have now the identity matrix. Identity, also known as unit matrix. Okay. So identity or unit matrix. So this is a diagonal or a scalar matrix in which the principal diagonal elements are equal to 1. Okay. So this is a scalar matrix. Scalar matrix with its principal diagonal elements equal to 1. Elements equal to 1. And it is represented by the alphabet capital I. Okay. Every time the same representation is used. Okay. So, and only one subscript is there to represent the order. So suppose we have I3, then this represents an identity matrix of the order 3. So this will be 1 0 0 0 1 0 0 0 1. So this is the identity matrix. If this is written as I2, then it will be a second order identity matrix like 1 0 0 and 1. So this is a scalar matrix with all the diagonal values equal to 1. So this is something known as identity or unit matrix. Next we have transpose of a matrix. Basically it is not a type of matrix, but we can put it here. Okay. So it will basically be used to define some other forms or types. Okay. So we have now transpose of a matrix. Okay. Transpose of a matrix. So we have seen that what is meant by transpose. So in transpose, the rows are transformed to columns or are converted to columns, and columns are converted to rows. Okay. So if the rows are, so this will be again for square matrix only. Yes. So even transpose can be for any other matrix also, non-square matrix also, but in that case the operations of determinant etc will not be applicable there. Only transpose can be achieved or can be done. Okay. So if the rows of a matrix are interchanged with columns, interchange with columns, then the new matrix which is formed is known as the transpose of the given matrix, okay, with columns. Then the new matrix formed is known as the transpose of the given matrix, okay. And the transpose is represented by a dash or prime symbol over the matrix name, okay. So suppose we have a matrix A which is, say, this is 1 2 3 7 8 9 2 3 4, okay. So in this case the transpose will be represented like this: a dash or a prime. Let me write it clearly. So a dash or a prime, okay, and this will be, this is sometimes also represented as AT, which represents transpose, okay. So this is, here the rows are interchanged with columns, okay. So 1 2 3 will now become column here, 7 8 9 is the second column, and 2 3 4 is the third column, okay. So this is known as transpose of the matrix, okay. So with this concept we can now understand what we mean by symmetric and skew symmetric matrices, okay. So next is a symmetric matrix. So symmetric matrix. So in a symmetric matrix, the transpose of the matrix is equal to the matrix itself, okay. And for this it will have to be a square matrix, okay. So square matrix, the transpose will be equal to the original matrix only and only if the order is same for both the original as well as the transposed matrix, okay. So a square matrix for which A is equal to A transpose, okay, for which the transpose is equal to the matrix itself is known as symmetric matrix, okay. So here A will be equal to A transpose, okay, for any given matrix, okay. So similarly we have skew symmetric matrix, okay. Skew symmetric matrix. So skew symmetric matrix is the one where A transpose is equal to negative of the matrix, okay, or means A is equal to minus of A transpose, okay. So a square matrix for which A is equal to minus A transpose, okay. And also remember the diagonal elements of a skew symmetric matrix will always be either 0 or complex, okay. So complex means purely imaginary, not actually complex, purely imaginary. Okay. So the diagonal elements of a skew symmetric matrix are zero or purely imaginary. Okay. Let me check for imaginary case. This will be zero, that's sure. So if this is iota and again iota, they do not need to be imaginary. They are zero. Okay. So the diagonal elements of a skew symmetric matrix are zero. Zero. Sorry, I said them to be imaginary. They are zero. Okay. And so this is symmetric and skew symmetric part. Similarly, we have another form or type which is triangular matrix. Okay. So let us see what is a triangular matrix. So triangular matrix, as the name suggests, will have a triangular kind of shape or form. Okay. So this is also sometimes known as echelon form. So this is a square matrix in which the elements either above or below the principal diagonal are zero. And based on the behavior, it will be upper triangular or lower triangular. Okay, so this is a square matrix, all of which or whose elements below the leading diagonal or above the leading diagonal are zero. So this is a square matrix, all of those elements above or below the principal diagonal are zero. Okay. So suppose we have a matrix A in which all the elements below the principal diagonal are zero. Okay, so suppose we have matrix 1, 2, 3, and say here we will have 0, then say 4, 1, then these elements will be 0, and here say we have anything, say 6. Okay, so this is an upper triangular matrix because uh, the elements above the diagonal are non-zero and below the diagonal are 0. So this is an upper triangular matrix. Similarly, there will be a lower triangular matrix. So let us see an example of that also. Okay. So suppose we have a matrix B in which the elements like those which are above the diagonal are 0. Okay, so this is a 3, this is 7, 1, and here we have say anything like 8, etc. So here we can see that the elements above the diagonal are 0 and lower elements are non-zero. So this is a lower triangular matrix. So this is lower triangular matrix. So this is something known as triangular matrix. Also, there are some spatial categories of matrices. Okay, so let us see them also. So, say next one is the orthogonal matrix. Okay, so we will quickly see them. Orthogonal matrix. Okay. So in this, whenever we have the product of A and A transpose as an identity matrix, then matrix A is known as orthogonal matrix. Okay. So square matrix A is orthogonal if A transpose is I. Okay. So this will be for orthogonal matrix. Okay. So this means that A transpose will be behaving as inverse of A. Okay. We will see in the upcoming discussion that what is meant by A inverse. Okay. So this is orthogonal, and next we have an idempotent matrix. Okay, so next is idempotent matrix. So what do we mean by idempotent matrix? Matrix, this is again a square matrix. Okay, so square matrix A is idempotent when or if A square is equal to A. Okay, means the multiplication of the matrix with itself results in the matrix itself. Okay, so such matrices are known as idempotent matrix. Okay, now again one more important class is the nilpotent matrix. Okay. Nilpotent matrix. So when square matrix is such that if it is being multiplied with itself, then after certain number of multiplications, it results into a null matrix. Okay, so uh, square matrix A is nilpotent with index k if A raised to power k is 0. Okay. Where 0 is a null matrix here. Okay. This is not the number 0, we can say it as O, where O represents the null matrix. Okay. And we have seen what is meant by null matrix. So K here will be the index of nilpotent matrix A. Okay. And similarly, there will be a class of matrices known as involutory matrix. Involutory matrix. So any square matrix A is known to be involutory if its square equals to itself. Okay, so a square matrix, say A again, is said to be involutory if a square is equal to pi. Okay. So it all the square always results in an identity matrix. Okay. When it was the square was resulting in the matrix itself, it was known as idempotent. And when it results in an identity matrix, then this is called the involutory matrix. Okay. And always remember that the identity matrix is always involutory. Of whether it be of any order, it will be involutory. Okay. And one more very important class is singular and non-singular matrices. Okay. So singular matrix is that so matrix square matrix is said to be singular matrix. Okay. So if the determinant of the matrix is 0, then matrix is known as a singular matrix. Okay. So a square matrix is a singular matrix, and this concept will be used in finding the inverse. Okay. So singular matrix if its determinant is 0, that is for a singular matrix the determinant of A is 0. Okay. And similarly there will be a non-singular matrix. Okay. So let us put them together. So non-singular matrix, here the determinant of A will not be equal to 0. Okay. So these are some important types of matrices. Now let us see some important operations of the matrices. So we will begin with the addition of matrices. So let us see. Addition of matrices. So suppose we have two matrices A and B and we want to add them. So for this we will have to add each corresponding element with uh, one another. Okay. And for the addition to take place, it is necessary condition that the order of both the matrices should be same, exactly same. Means the number of rows and number of columns should be equal in both the matrices, because there is element to element addition here. Okay. So for addition, we can write this as if say we have if A and B are two matrices of same order, or two matrices of same order, then their sum is defined as the matrix in which each element is sum of corresponding elements of A and B. Okay. Then their sum say C is defined as the matrix in which each element of each element is in which each element is the sum of corresponding elements of A and B, is the sum of corresponding elements of A and B. Okay. So we can understand this with the help of an example. Okay, so suppose we have a matrix A which is given as say 4, 2, 5, and we have 1, 3, -6, and we have another matrix which has elements like 1, 0, 3, then 2, 4, 6. Okay. So the sum matrix C will be nothing but the summation of corresponding elements. So this is say 4 to 5, 1, 3, -6, and this was 1, 0, 3. This is 2, 4, 6. So we need to add the corresponding elements. So this is 4 plus 1, this is 2 plus 0, this is 5 plus 3, this is 1 plus 2, and 3 plus 4, then -6 plus 6. Okay. Like this. Okay, so this matrix C will become 5, 3, 2, 7, 8, 0. Like this, we do the summation or addition of matrices. Okay. And remember that the order of both the matrices need to be same for addition to take place. Okay. So let us see the properties of addition. There are laws like commutative law and associative law which are valid for addition, and same goes for subtraction also. So subtraction follows the similar rules in case of matrices like that of matrix addition. Okay, so we have properties of matrix addition. Properties of matrix addition. Okay. So what we will have, firstly, matrices of same order only can be added or subtracted. So matrices of only same order can be added or subtracted. Okay. And apart from this, there is the commutative law which is valid. So commutative law is valid, which means that matrix A plus B will be same as B plus A. Okay. Or this can be even subtraction. Okay, so commutative law is valid. Again, here the associative law is also valid. Okay. So associative law is valid. Okay. So what does this mean? It means that suppose we have A plus minus B plus minus C. This will be same as A plus minus B plus minus C. Okay. So associative law is also valid here. Okay. So these were some properties of matrix addition. Now let us see the scalar multiplication of matrices. Okay, so there is a difference between the matrix multiplication and scalar multiplication of matrix. So matrix multiplication basically means multiplication of a matrix by another matrix. Okay, but here in scalar multiplication, we will multiply scalar what is happening? Scalar with the matrix. So scalar multiplication of a matrix. So what happens here is simply when scalar value is multiplied to a matrix, then it gets multiplied to each and every element of the matrix. Okay. So this rule or the scalar multiplication of the matrices says that if matrix is multiplied by a scalar multiplied by a scalar, then each element of the matrix is multiplied by k. Scalar k, then each element of the matrix is multiplied by k. Is multiplied by k. Okay. So how is this done? So let us understand this with the help of an example. So say we have a matrix A, which is nothing but say 1 4 7 3 2 8 6 7 4. Okay. And suppose we multiply this matrix by some scalar value, say 3. Okay. So we have 3a will be equal to 3 into this matrix 1 3 6 4 2 7 7 8 4. Okay. So as we have mentioned that each element of the matrix will get multiplied with the scalar. Okay. So this becomes 3 12 21 9 6 24 18 21 12. Like this, each and every element of the matrix is multiplied by that scalar value. Okay. So this was something called scalar multiplication. So let us close for now, and in the next class we will see the matrix multiplication, which means the multiplication of a matrix by another matrix. Okay. So see you in the next class. Thank you.